Okay, well, it's my great pleasure to welcome Allison Miller for the seminar today.
Thank you. I'm very glad to be here and have the opportunity to talk with you all. So I will do my best to keep an eye on the chat, but also please feel free to just unmute and ask if you have any questions. So I want to tell you about examples of negative amphichiral knots with large 4 genera. And to start off, I want to remind you or tell you that we always think about, given a knot K in 3-dimensional space, we're always thinking about both the knot K and the 3-manifold S3 as having orientations of their own. And so by reversing one or both of those orientations, we get up to sort of 4 different related knots. And so if K is the original, if we reverse the orientation on K, we get K reverse. If we reverse the orientation on S3, we get what's called the mirror. And then these two operations commute. So there's sort of a single mirror reverse knot, which it's popular to call, at least if you like concordancy things, minus K. And so we say that a knot is negative amphichiral if these two, if K and its mirror reverse are ambiently isotopic. And whenever I write equals for knots, I mean are ambient isotopic. Okay. And we'll come back to more examples of this later. So secondly, one of the big ideas of the talk is the idea of a knot being slice. So over here on the right, I've drawn a little schematic picture where we have S3 bounding the 4-ball, the knot K living in the boundary. And we say that K is slice, well, if there exists an embedded D2 in B4, so sort of schematically, here's our D2, such that the boundary of D2 is the knot K. So such that the boundary of the pair, let's say B4, D2, is just S3 and K. And so really I should be telling you I should be being a little bit more specific. What do I mean by embedded in B4? Do I just mean a continuous map, a smooth map, a locally flat map? And for everything I say today, you can choose as you prefer, smooth or locally flat. Smooth is easier to visualize, so unless you have a strong preference, I would go with that. So this is sliceness, or we think about it as being 4-dimensionally trivial. And that you can generalize that idea a little bit by having a measure of the 4-dimensional complexity of a knot. And so the 4 genus, or 4-dimensional complexity of a knot, is the minimal genus of a surface F, where basically the same picture is going on, where F is embedded into B4, and the boundary of F is the knot K. And again, you can think about either the smooth or the topologically locally flat 4 genus, and everything I say today will hold in either of those 2 categories. So think about whichever you prefer.
F orientable?
Yes, yes, definitely. I would not want to define the genus of it otherwise, but yes, yeah. You can also talk about the non-orientable 4 genus, where you sort of weaken that, but much less is known, particularly in the locally flat category. In fact, I don't even think we have any examples of knots with arbitrarily large, non-orientable, topologically locally flat 4 genus, which is a bit of a mouthful, but it's much harder. All right. So, other questions? So what I now want to do is talk about 3 different approximations to sliceness, or 3 different qualities that you might say makes a knot slice-like. And then the goal of the talk is to describe to you why there are examples of knots which are slice-like in all of these 3 senses, but still have large 4 genus. So still are far away from being slice as measured by genus of surfaces. So the first one is maybe the least likely that you've heard of it before, and it's rationally slice. And so a knot is rationally sliced. What I'm going to do is repeat almost the same definition, but I'm going to change the four manifold that the disk is allowed to live in. So we say that K is rationally sliced, and still I only am thinking about knots in S3. So K is rationally sliced if there exists a disk embedded in some four manifold, such that, well, first of all, it's a slice disk for K in the sense that the boundary of the pair W4 and D2 is the pair S3K. And secondly, that the homology of W with rational coefficients is the same thing as the homology of B4 with rational coefficients. It's like, in a certain sense, if all you know about is rational homology, that's your only way of recognizing whether something is a four-ball, then it's slice. And we'll see some examples later on of knots that are rationally sliced but not slice. It turns out those are not hard to procure examples of. The next approximation to sliceness one might like is being two torsion, or indeed torsion. And so what do I mean by that? I mean that K is two torsion, and this has its precise sense, two torsion in a concordance group, but you don't need to know the definition of the concordance group for this. It's two torsion if K connects some K is slice. So again, you know, the knot might not be slice itself, but it's close to slice in this sense. And so you might well wonder, why am I not just saying torsion, that a knot is torsion if some connected sum of it with itself some number of times is slice? And the answer is that as far as we have been able to tell, the only kind of torsion we see is two torsion. That's an open question. There's no proof or anything close to a proof of it, but we certainly haven't found any examples yet. And so my final approximation to sliceness has to do with diagrams and crossing changes. And so this one is maybe the least topological and most diagrammatic of all of them. So the last option is, given your knot K, you can transform it to a slice knot by doing either positive to negative crossing changes, so choosing some number of positive crossings, which are oriented like this. And remember, everything is oriented, so that's fine. And changing them to negative, or vice versa, taking a bunch of negative crossings and changing them to positive. So a comment, you can unknot any knot by changing a bunch of crossings. So if you're allowed to mix both positive and negative crossing changes, then this would be sort of a trivial thing to say. But here I'm saying, well, there's one way to get to a slice knot just by changing positive crossings. And there's another way to get to a slice knot just by changing negative crossings. So you could think about this first condition, you know, just plus to minus, as being somehow more positive than a slice knot. And the second one is being more negative than a slice knot. And so again, this gives us sort of a diagrammatic idea of being close to slice.
Hold on, just to check, you're using a different definition of either or here.
Or, yes, by both.
Okay, yeah.
Yeah.
So I was going to say, you otherwise, yeah, okay.
Yeah, thank you.
Okay.
Yes, you can do it both ways. Great. Yes. So let me tell you an example, which is the figure 8 knot. And so let me start with the last one, which can be transformed to slice by changing either positive to negative or negative to positive. That one's the easiest to see here. If you change that crossing, you get an unknot even. And that crossing it appears to be negative. Also, if you change this crossing, which is positive, you get the unknot. So that's relatively nice. And then for the justification that this is rationally slice, and 2 torsion, I actually want to tell you about a result that's a little bit more general, which states that all 3 of these conditions approximating to sliceness can be implied by something else. Okay, so this is the proposition, which I will unpack momentarily. So suppose K is what's called strongly negative amphichiral, and I'll tell you the definition of that. It's a little bit more than amphichiral, and can be transformed to a slice knot by changing plus to minus crossings. Then 1, 2, and 3 all hold. I will say this is sort of overkill for getting any of 1, 2, and 3 individually, but to get all 3 at once, this is an easy way to do it. So let me remind you, or let me tell you about what strongly negative amphichiral was. So negative amphichiral was just that a knot is isotopic to its mirror reverse. To be strongly negative amphichiral, in some sense, means that there's an involution demonstrating that for you, an involution of S3. In particular, a knot is strongly negative amphichiral if there's an orientation reversing homeomorphism of S3 that takes the knot to itself and that squares to the identity. So what's an example of that? The figure 8 knot is sort of the quintessential strongly negative amphichiral knot. It's a little bit harder to see from this upper picture, but if we take this diagram, and remember, maybe this diagram on S2 is the right way of thinking about it. Well, what you can do is first rotate 180 degrees about the marked point, and then reflect in the plane of the diagram. So I'll pause for a second to give you a chance to imagine that. Rotate 180 and then reflect. So that is an orientation reversing map of S3. It certainly takes the knot to itself, and it squares to the identity. And so, as a note, strongly negative amphichiral certainly implies negative amphichiral. But the converse is not true, though that took some time to prove. Okay. Any questions?
Can you remind us what was number 3 operation?
Yes, the number three was changing to slice by either plus to minus and minus to plus.
Yeah, but the name you gave initially on the previous sheet, previously, yeah.
This picture?
No, just.
Sorry, I'm not quite understanding what you mean.
Oh no, that's all right. All right, thank you. Yep, it's good.
Okay. And so let me tell you about the proof of this proposition that tells you that strong negative amphichirality guarantees plus this guarantees the 3 conditions that we care about. The most interesting part of this proof is that strongly negative amphichiral knots are rationally slice. And I'm not going to go into the details of this. I'm just going to tell you sort of the big picture idea. So what you're going to do is build the rational homology ball in which K is slice. And you're going to do so from first, so let me tell you what this is. You look at the 0 surgery along K. Convince yourself that you can extend the involution that we know exists on S3. Well, okay, you can restrict it to the knot exterior, certainly, and then you extend it to the 0 surgery. And you can do so in such a way that is still an involution. And so now take the quotient. Okay, great. So you have this strange non-orientable 3-manifold. And now what you need to do is take the non-orientable, the non-trivial interval bundle over it, is one way to say this. That's an orientable 4-manifold. That's really all I want to say about this, except that if you, in a careful way, glue on D2 cross D2 to it, then this is the W you need in the definition of rational. You should be, if you haven't seen this before, it's not at all entirely immediate. One comment, though, to the experts is that this is really the slice disk exterior. And you should really think about this as gluing on a neighborhood of the slice disk. And so it all works out when you build this four manifold. The boundary is S3. You have attached this D2 cross D2 in such a way that it very clearly contains a core D2 that's a slice disk, and then you compute homology. And that's due to Kawauchi. And so 2 is that the knot is two torsion, i.e. K connects on K is slice. Well, since K is strongly negative amphichiral, it's negative amphichiral. And so that tells us that K is ambient isotopic to the mirror reverse, minus K. Okay, well that gives us certainly that if we connect some with K on both sides, that's ambiently isotopic to K connects some minus K. And this is well known to be slice. The whole reason why we use the notation minus K is to remind ourselves that it's the concordance inverse of K. And then finally, what was 3, that either by positive to negative or negative to positive crossing changes, we could unknot. Sorry, we could not unknot. We could take K to a slice knot. And well, we sort of cheated on this one. We assumed half of it, that we could transform K to a slice knot by changing positive to negative crossings. And now we just apply our negative amphichirality and say, okay, so apply that and then do the corresponding crossing changes. Great. Questions at this point?
Yeah, so that first condition isn't using this condition about crossing changes. That's just, you're just claiming that every strongly negative amphichiral knot is rationally slice.
Yeah,
Okay.
yeah. 1 and 2 are both have sort of nothing to do with the crossing change. I just bundled it all together.
Okay.
I should note as well that until very recently, it was open whether all rationally sliced knots were strongly negative amphichiral, or a little bit more precisely, whether all rationally sliced knots were concordant to strongly negative amphichiral knots. But it turns out that's not the case due to very recent work of Halm and others, joint work of Halm with others. In particular, if you take the figure 8 knot and take N1 cables of it, it's not too hard of an exercise to show that those knots are still rationally sliced. They're certainly no longer strongly negative amphichiral, but the hard work is to show that they're not even concordant to strongly negative amphichiral knots. And the way they do that is by showing, in fact, that they're not two torsion anymore, that they are infinite order elements in concordance. That's a side note, but I think it's a very nice result. The N should be odd, or you get into some confusing questions. All right. So here's the new goal, which is, again, our old goal was just to find knots that are close to slice-like, and yet have large 4 genus. But now it's, because of this proposition, I want K to be strongly negative amphichiral. I want K to go to a slice knot via positive to negative crossing changes. And finally, I want K to have large 4 genus. So I should sort of pause for a second to say that why are we able to, for example, show that there are knots that are slice-like in this sense, but not slice? And my answer to that is the Alexander polynomial is a really great abstraction. So in particular, if I just sort of rewind briefly to the figure 8 knot, that guy has Alexander polynomial, which is t squared minus 3t plus 1. And so one of the oldest sliceness abstractions due to Fox and Milner says that if you're slice, your Alexander polynomial factors in a certain way. This polynomial is irreducible, so the figure 8 knot is not slice. But this kind of abstraction, Alexander polynomials don't tell you anything about 4 genus. You can have a very large, very complicated Alexander polynomial and still have 4 genus equal to 1, for example. So this is our goal. And why is this at least somewhat challenging? Well, for almost all of the known lower bounds on 4 genus, and indeed almost all of the sliceness obstructions we have, if K is minus K, so just even non-strongly negative amphichiral, then these invariants have to vanish. So let me just go through these really quick for those who are curious. The first one is the Tristan-Levine signature function. So a very classical invariant that gives lower bounds on the 4 genus. The next slew comes from Hagard-Floor homology, and the last few come from Kavanagh homology. I should say, in general, strongly negative amphichiral is overkill. Some of these are directly implied to vanish just from being rationally sliced, though I believe the Kavanagh homology ones are open. Just generally speaking, all of these conditions tell you that a lot of invariants have to vanish. And I mean, really, the proof of this is to say that sigma of K then has to equal sigma of minus K. And this usually equals minus sigma of K. And even when it doesn't always equal that, you can still sometimes use the negative chirality to force vanish. Okay, so what's left? I said that this was an almost complete list of lower bounds on the 4 genus. But what's left is actually something that we've known about for quite a long time, which are Casson-Gordon signatures. And I will warn you here that if you are an expert in Casson-Gordon signatures, I'm going to slightly blur the distinction between 2 different types, the 3-manifold invariant and the non-invariant. If you would like to ask me where the blurring occurs, please feel free. Otherwise, if you do not know the definition of Casson-Gordon invariants, please just feel free to ignore everything I just said. Okay. So these are not entirely delightful to define, but what are they? Well, they depend on a lot of choices. So in particular, if I choose a knot, I choose 2 natural numbers greater than 1. And finally, just as a note, well, I look at the n-fold cyclic branched cover. And I look at a map on its first homology. And to get interesting results, I want n and q to both be prime powers, though they're defined either way. Okay, so with all of these this setup, what do I get? I get a rational number. So briefly, to tell you the idea of how these are defined, you need to find some 4 manifolds. You need to find a 4 manifold whose boundary is the cyclic branched cover, or maybe some multiple of it. And then you need to extend the map chi over the 4 manifold. And then once you've done that, you're going to look at the twisted intersection form on second homology and compute some signature. This is sort of, I'll leave it at that. Please feel free to ask questions. So what I want to emphasize here is that Casson-Gordon signatures, sort of as is clear from the definition, they don't just depend on the knot K. You have to choose a character. By the way, if you choose the trivial character, you always get 0. So that's not a great choice. And so this makes them somewhat maybe more of a hassle to work with. No single Casson-Gordon signature gives a sliceness obstruction, for example, let alone a 4 genus bound. But that is actually exactly why they turn out to be helpful in this case. Sort of this added complexity means that a knot being isotopic to its mirror reverse doesn't force the Casson signatures to vanish, it just forces a kind of symmetry. So let me show you an example, which is, here's the figure 8 knot, our old friend, and its double branch cover is the lens space. So in particular, the first homology of the double branched cover is order 5, which means that there are 5 characters to anything interesting. And so you can compute, well, okay, I told you already that with the trivial character, you get 0. So choose a non-trivial character, and you can choose a non-trivial character so that you get 1/5 as the corresponding Casson-Gordon signature. That's just a fact that I'm telling you. Okay, and there are some symmetries of Casson-Gordon signatures. Since 4 equals -1 mod 5, this also equals 1/5. And now, actually, you can figure out the rest of the table by using the fact that K is negative amphichiral. That tells you that these are going to be -1/5 and -1/5, respectively. The key takeaway from this is not these precise numbers, but just what I said before, that being a negative amphichiral knot just implies that the set of Casson-Gordon signatures has some interesting symmetry. Not that all are 0. Or in fact, it doesn't imply that any of them have to be 0. And so that sort of gives you a little bit of leverage here. So just 2 other nice features of Casson-Gordon signatures. Well, first of all, provides lower bound on the, in fact, topological and therefore also smooth 4 genus, and that's due to Gilmer. I would be happy to state the precise formulation if anyone would like me to. It's a bit of a mouthful. But the sort of takeaway is if G4 is small, then for some characters, the absolute value is also small of the Casson-Gordon signature. Here, this sort of the number of some depends on the genus. So does what I mean by small. So this is very imprecise, but often workable. And then secondly, something that's very handy, often in terms of cooking up examples and actually computing things, is that there are formulae for the Casson-Gordon signatures of satellite knots. And so that lets you sort of, in terms of Casson-Gordon or even Tristram-Levine signatures of their constituent pieces. So they're really, really powerful. If you want to build an example of a knot with certain properties, with having certain Casson-Gordon signatures, often you can do so just by various satellite constructions. Other questions about, any questions about Casson-Gordon signatures? I've been very vague. Okay, so now what I want to do is tell you a little bit about the proof of the main theorem, which I appear to have forgotten to write. But it's short, so it can go here. So for any G, you can find a knot KG, actually infinitely many, which are linearly independent in the right sense because they're going to be 2 torsions, so they're not really linearly independent. So such that KG is strongly negative amphichiral. We know that we can transform KG to a slice knot by a bunch of positive to negative crossing changes, and such that the 4 genus of KG is strictly larger than G. So we can do what we want to do. We can find these examples of knots which are slice-like in these 3 senses, and yet which have large 4 genus. And so now I'd like to tell you about these knots and a little bit about the proof in my remaining time. Okay. So we're going to take a connected sum of satellite knots. So let me sort of first tell you about this picture here. I've shaded in orange a genus 1 surface, the boundary of which is our knot S of Ji. And what you need to do is, if you haven't seen sort of this notation before, these boxes indicate that I need to tie the band of the Seifert surface into the knot JI or the mirror of JI respectively. And so this is an iterated satellite knot. By the way, just as a note, you can check that if I plug the unknot in here, I get the figure 8. So these are generalizations of the figure 8. And they're carefully chosen generalizations. In particular, S of JI is always strongly negative amphichiral. And you can see that from the same picture as was used for the figure 8 knot. It's the same. If you modify this diagram a little bit, you can do the rotation and reflect trick. So one of the reasons, okay, so to sort of belabor the obvious for a moment, we can't just take large connected sums of a fixed S of J if we hope to construct something with large 4 genus, because S of J connect sum S of J is always slice. So what we're going to do is we're going to choose JI so that they're increasingly complicated. And I'll be a little bit more precise about that later. So we're going to take our K, our KG, to be the connected sum of 2G plus 2 of these knots, where we've chosen the JIs to be increasingly complicated as measured by the Tristram-Levine signature function. And I'll say more about that later. And also at one point, we're going to need reversible. As a side note, there are some very nice results that basically allow you to realize if you have a given hypothetical Tristram-Levine signature function that you would like to realize as the Tristram-Levine signature function is a knot, you can always do so. There are very few constraints that all such functions must realize, but once you meet those constraints, you can just do it. So that, again, allows you a great deal of flexibility. You get to pick your Tristram-Levine signature function. And the reversibility, in our case, is not a constraint. We're going to, in fact, be able to, if we wish, take JI to be a large connected sum of 2 5 torus knots, for example. I mean, yeah. 5 here doesn't really matter. It could be anything bigger than 3. So I need to tell you that why this knot KG satisfies the 3 strongly negative amphichiral, change to slice by positive to minus, and has large 4 genus. So I've already sort of told you how to see the strongly negative amphichirality. It's a very diagrammatic picture. So how do I change this knot to a slice knot? By making positive to negative crossing changes. Okay. So first, let me tell you what crossing I want you to change. In fact, a single crossing is going to suffice. And it's this one. Okay. So that is in fact a positive crossing. If you trace out the orientations, it looks like this. And if I change that to a negative crossing, I get what I'm going to call S of J minus. And what I need to do is convince you that S of J minus is in fact a slice knot. And so this is actually why I've kept this genus 1 Seifert surface around. So let me tell you about a nice way to prove that a knot is slice. So my claim is that S of J minus is slice. And so I've drawn this curve in purple, gamma minus. And so there are 2 things I want to tell you. So first of all, you can just check that gamma minus is 0 framed by the surface in the picture. If you push it off in the surface or orthogonally to the surface, you get 0 linking number algebraically with the original knot. The other thing that's true is that as a knot in S3, this is isotopic to J connect sum the mirror of J reverse. And here that reverse is popping up sort of because we went through J one way and we went through the mirror of J the other way. i.e. J connects sum minus J, and this we know is always slice. So now my claim is if you have a knot that bounds a genus 1 ciphered surface, and if you find a zero-framed curve representing a non-trivial element of first homology that itself is slice, then the original knot, in this case S of J minus, must be slice too. And so the proof of that is this picture. And so let me sort of expand on what I mean by that. So what have I done? This is a schematic where S3 is over here at the left. We have S3 bounding before. Our knot S of J minus is sitting in the boundary S3. And I've pushed the interior of the surface F into the interior of the 4 ball. And the curve gamma minus sort of goes along for the ride. But now I know that gamma minus is slice. So what I'm going to do here is I'm going to cut out a tubular neighborhood of gamma minus from the surface pushed in F. So what do I see? Well, I see a pair of pants now. Sort of gamma minus 2 copies. And now the fact that gamma minus is itself a zero-frame slice knot allows me to glue in the slice discs, 2 copies of the slice discs, like so. And so pair of pants with 2 discs glued on, that is itself a slice disc. So this is how you can build a slice disc for S of J minus. Any questions about that? Okay. So we actually don't need to prove the negative to positive crossing also gives you a slice knot. Because of the strongly negative amphicirality, we get that for free. But why not just take a look at it? It's a nice picture, and it tells you why I needed this condition of reversibility. So here, again, same knot drawn. Now we change this crossing, and we get this picture. And we choose a slightly different curve. Again, now this curve is zero-framed by F. It's a different F. That's slightly confusing notation, but the curve is zero-framed by it. But this time it is isotopic to J connects the mirror of J. But we chose J to be reversible. So this is the same thing. As this, which we know to be slice. So we can use the same argument again here. All right. Any questions? Okay, then I'll spend my last few minutes saying a little bit. So as I mentioned before, we're going to take Kg to be the connected sum from I equals 1 to 2G plus 2 for S of Ji, where Ji is chosen in a particular way. So in particular, what I want to tell you about is, okay, I promised that Casson-Gordon signatures were the key invariants here. So what are the Casson-Gordon signatures of these Kji? What do they look like? Sorry, these Kg. So first of all, the useful fact one I'm going to say is that Casson-Gordon signatures are additive with respect to connected sum. So there's some kind of canonical identification such that the Casson-Gordon signatures of Kg with what I'll just write as a tuple chi1 to chi2g plus 2. So implicitly here, I am identifying characters on the branched cover of Kg with sort of tuples of characters, one on each of the branched covers of S of Ji, but I can do that. And under this identification, I just get oops. So my goal is going to be to show that I can choose these knots ji so that for, in fact, any, so my goal is to pick these ji knots such that this term is large relative to the genus for any non-trivial list of characters. And so here, I don't get to assume that all of them are non-trivial. The non-triviality of this tuple means that at least one of them is non-trivial. And so what I'm going to do, and what I'm able to do, is to choose the ji so that these terms here are increasingly large. And what do I mean by that? Sort of if you look at what's the last I, such that chi I is non-zero, that term is just going to dominate everything that comes before it in absolute value. In fact, it's going to dominate the sums of what comes before it in absolute value. And so as long as one of these characters is zero, you're sort of guaranteed this largeness. But now we need to see that that's possible. And again, this is really, let me come back and steal a picture as well as come back to the figure 8 knot and look at it for a second, since this really is a generalization of the figure 8 knot. Here we got 1/5 minus 1/5 minus 1/5 1/5. What we really want to do for these satellite knots is improve this to 0, some big constant c. That's going to have to be there and there. And then because of the negative Amphichirality, we do have to get negative c's there, more or less. And again, this is where I'm slightly lying about Casson-Gordon signatures. So remember that this is our S of j. So here are some facts for you. And these are the key facts that we really need. So the first one is that the homology of, let's just go with the double branched cover of S of j equals the first homology of the double branched cover of S of u. And this comes from the fact that sort of this is governed by the Seifert form, if you want to think about it from that perspective, and the Seifert form of S of j and S of u are the same because we've just sort of tied flat knots in these bands. So in particular, this is Z mod 5c. And so the second thing we need to know is what is the Casson-Gordon signature of S of j with respect to one of these characters. It says that first you're going to get a contribute negative 1/5 if it's non-trivial, or 0 if it's trivial. And now both j and the mirror of j are going to contribute pieces. And the key reason, I mean, you could work, let me go. So it's plus the signature of j at, here I'm choosing W5 to be sort of the first fifth root of unity. And then we get a term coming from the mirror image of J to twice that. And the way, okay, how do you get this equation from Litherland's result? You really have to understand, let me just slightly erase this. You really have to understand how these two curves lift to the homology of the double branch. But one can do that. And so let me just rewrite this a little bit. Well, we have this term coming from the base knot S of U, and again, that's small. And then we get plus sigma j of omega 5. There's some A here. And then properties of the Tristram-Levine signature, we get minus the signature of J at omega 5 to the 2 pi. And so here, the key feature is really that you can make these two terms not cancel each other out, so long as these two signatures don't equal each other, and there's no reason they have to. These aren't in particular, let me just draw a quick unit circle over here. Oops. We see, this is not going to be an attractive drawing. Let's just very schematically, we see something like this. And the symmetries of the Tristram-Levine signature function, they tell you that these two signatures have to be equal, and that similarly, these two signatures have to be equal, but they don't force these two signatures to be equal. And in fact, you can make them wildly different by appropriately choosing your knot. And so that's exactly what you need to do in order to get this term large. And so that is sort of the key last step of the proof, is just choosing those knots carefully. And I will end there. Thank you very much.
So my understanding here was, well, actually, does anyone else have any questions before I pile in?
Oh, wait.
I mean, I was just going to say, I mean, my understanding that the open problem here was just exhibiting sort of negative amphichiral knots with large 4 genus. I mean, is this stuff about crossing changes? This is your embellishment, isn't it?
Yeah, this was actually, that part of it came out from a conversation I had with Jung-Hwan Park, who, so incidentally, you can, let me just write this really quickly. For a general knot K, you can look at C4 of K, which I'm going to say is the minimal number of crossing changes needed to take K to slice. And you can similarly define C4 plus to be the minimal number of positive crossing changes, where here note any number of negative to positive is okay, just not counted. And C similarly, so you get that C4 of K, I mean, very much by definition, that C4 of K is at least C4 plus C4 minus. And you know that this isn't always equality, because figure 8 has 0 here and 0 here, but 1 here. So there's sort of another maybe related question, which is, can this difference be arbitrarily large? And these examples also show say yes to that, because these examples still have 0 here and 0 here, but we also have this bound on the 4 genus. So since they have large 4 genus, they have large crossing change number. And so it was frankly really just serendipitous that these examples that sort of I cooked up for answering the 4 genus question also sort of just worked for this crossing change question.
So is there any, I don't know, moral reason why, intuition you offer about why Casson-Gordon invariants seem to have like the right mismatching of behavior that just doesn't work in some of the more modern theories?
I mean, so I am not a Haggard floor modern theory person, but I will say that somehow the key ingredient is the complexity, is that you have multiple Casson-Gordon signatures and no one of them is a sliceness obstruction. So for example, you know, if D invariants of branched covers gave a lower bound on the 4 genus, which I don't think they do, then if they did though, they have the right kind of complexity. They could, if they gave a lower bound on the 4 genus, they could give a similar result, I think, because again, there's a whole slew of them. And the negative antichirality is just going to mean, well, that they get paired up positive and negatively, maybe, not that they all vanish.
Gotcha.
So yeah,
Okay,
complexity is good, is maybe the moral.
Right. So in that way, it feels a little reminiscent of, like, in terms of like playing up that complexity, like, I don't know, the way people obstruct, whether it's like homology concordance or one of these things, like sort of when you have a slew of variants which are going to start going off in different directions. Okay, interesting. One other question if I could ask real quick is, the examples you mentioned of the Hom and her collaborators for rationally sliced but not, I believe, not finite order. Is anything known about the genus of those?
No, so that's a great question. So no, they don't know that the genus of theirs is large or small. Interestingly, they have small topological 4 genus. I don't know. Okay, I think that's slightly interesting. You can, so for example, candidates for large G4 plus rationally slice plus infinite order in concordance might, if I had to choose candidates, what I would do is I would take the M1 cables of these knots, because that would get you, in fact, you can, by choosing M appropriately here, you get big G4 and rationally slice for free. And then Homs were, you know, they just used the figure 8 knot. I don't see any reason why using more complicated connected sums of satellites would all of a sudden make that finite order. So presumably that's also true. It's just, you know, I think it was a beastly computation as it is. But yeah, I think these should be examples.
That makes sense. That makes sense. Thanks.
Proving it, yeah.
Well, if there are no other questions, let's thank Allison again.